If the scale of what's unfolding in our upper atmosphere right now got you locked in, take a second and hit subscribe to Orbital View. We're tracking Solar Cycle 25's peak in real time, and the story keeps getting bigger. Drop a comment with this question: does your work or daily life depend on GPS, satellite communication, or aviation? Because what we're covering today is going to hit differently depending on your answer. I read every one. Here's what we're getting into: a solar cycle that every major forecast said would be quiet, and turned out to be one of the strongest in 60 years. A layer of our atmosphere currently running temperatures that no satellite was designed to survive. And a question that neither NOAA nor NASA has answered publicly. If the models were this wrong about the cycle's strength, what else are they underestimating about what it does to the systems we depend on? Let's get into it.
Let me start with a number: 115. That is the smooth sunspot number that an international panel convened by NOAA, NASA, and the International Space Environment Services predicted Solar Cycle 25 would reach at its peak. They published that forecast in 2019. 115, they called it. Average cycle, quiet maximum. Nothing to worry about. The actual number as of late 2024 was 216, not smoothed, not a momentary spike. 216, the highest single monthly count this cycle, roughly double what the most authoritative solar prediction apparatus on Earth said was coming. And here's the thing I need you to hold on to from the very start of this investigation. That gap between 115 and 216 is not just a statistical error. It is a policy failure, a planning failure, an infrastructure failure that is unfolding right now in real time across every altitude of Earth's atmosphere. And most of the people managing the systems at risk have no idea the baseline assumptions underneath their safety margins just got shattered. Solar Cycle 25 began in December 2019, right at the edge of the COVID-19 pandemic's opening months. The timing meant that the solar prediction community's revised forecasts got almost zero public attention. The NOAA Solar Cycle Prediction Panel had gathered its experts, run its models, and arrived at a consensus: weak cycle, modest impact, peak in July 2025, plus or minus 8 months, with a maximum smooth sunspot number of 115. They called it average in intensity, and similar to Cycle 24. Cycle 24 had been the weakest solar cycle in 100 years. That framing shaped decisions. It shaped satellite design margins. It shaped orbital decay models. It shaped how much operational buffer spacecraft operators built into their contingency plans. It shaped, in ways that are only now becoming visible, how much resilience we did, and didn't, put into the infrastructure that lives in and around the upper atmosphere. And then the sun did not cooperate. By January 2023, Solar Cycle 25 had already surpassed Cycle 24 at the equivalent point in the previous cycle by 12% more daily sunspots. Not a little stronger, measurably significantly, unambiguously stronger, and rising. By April 2024, complex active regions were driving daily sunspot numbers above 250. By October 2024, the cycle had produced its strongest flare yet, an X 9.0 on October 3rd. The research community scrambled for frameworks. The Astrophysical Journal Letters published a new analysis in January 2025 by Baolin Tan, Yin Zhang, and colleagues warning that the most powerful flare classes, X10 and above, what the field calls S-flares, were likely still ahead, probably clustered in the descending phase after 2027. And from early 2026, the pattern has continued. Region 4366, a relentless active sunspot cluster, dominated solar headlines through February, and NOAA's Space Weather Prediction Center has been issuing Type 2 radio emission alerts associated with coronal mass ejections into May 2026. But here's the part that most coverage has missed entirely. The sunspot count is not the story. The sunspot count is just the messenger. The story is what extreme solar activity does to the layer of atmosphere sitting between the surface and space, and what happens to everything we've put up there when that layer behaves in ways no one planned for. The thermosphere, that's where this investigation actually lives. Most people have never thought about the thermosphere in their lives. It sits between roughly 85 and 600 kilometers above the surface. Below it is the mesosphere, the layer where meteors burn up. Above it is the exosphere, which fades gradually into the void of space. The thermosphere itself is, depending on how you measure it, simultaneously part of Earth's atmosphere and part of what we casually call outer space. The International Space Station orbits inside it. The Starlink constellation lives inside it. GPS satellites transit through and above it. And the thermosphere is by a wide margin the most violently variable region of Earth's atmospheric system. During solar minimum, when the sun is quiet, Exospheric temperatures at the top of the thermosphere run around 700 Kelvin. During solar maximum, those temperatures climb to 1400 Kelvin or higher. That is not a small change. That is roughly doubling the thermal energy in a layer of atmosphere that directly governs the drag forces on every satellite in low Earth orbit. And during solar cycle 25, the thermosphere is not behaving like a quiet, average cycle. It is behaving like the sun that actually showed up, the one nobody predicted. The Thermosphere Climate Index, which NASA's timed satellite has been measuring since 2001, registered a near 20-year temperature peak in 2023. And that was before the cycle's most intense period. Martin Blinchak at NASA Langley Research Center, one of the lead scientists on thermosphere monitoring, described successive geomagnetic storms in early 2023 as stacking energy into the thermosphere faster than the atmosphere's natural coolants. Carbon dioxide and nitric oxide could radiate it away. When the storms come back to back, he said, the temperature stays high. And solar cycle 25, at its observed strength, has been producing those back-to-back storms at a rate that was never baked into the planning models. So, the question I'm going to spend this entire investigation answering is not whether the thermosphere is heating. It is, dramatically measurably, with specific numbers and specific instruments tracking it in real time. The question is what that heating does to our satellites, to the orbital debris field, to the navigation systems that every aircraft and every autonomous vehicle on Earth depends on, when the cycle driving it was underestimated by a factor that has no precedent in the modern observational record. That is the story. And it starts with understanding exactly what the thermosphere is, why its expansion matters at scales that reach the ground, and why the systems that are supposed to protect us from the consequences of extreme solar activity were calibrated against a sun that turned out to be a fundamentally different sun than the one we actually got. Picture the atmosphere as a giant balloon. The surface is inside, looking out. The skin of the balloon is the thermosphere, the outermost layer of any meaningful atmospheric density before you hit the empty of space. Now picture someone turning up the heat on the outside of that balloon. The skin expands, it pushes outward. And everything that was sitting in and around that skin, every satellite, every piece of debris, every piece of orbital infrastructure, suddenly finds itself in a denser environment than it was before. That is, in rough terms, what happens when extreme ultraviolet radiation from the sun hits the thermosphere. The EUV photons, wavelengths between 1 and 120 nanometers, are completely absorbed above 80 kilometers. None of them reach the surface. The thermosphere eats all of it. And when it eats more of it, it gets hot, and when it gets hot, it expands. NOAA's Space Weather Prediction Center is explicit about the mechanism. Solar EUV irradiance, they state, varies by as much as an order of magnitude on timescales of minutes to hours during solar flares, days to months as active regions rotate across the solar disk, and years to decades across the solar cycle. That variability drives the thermosphere and ionosphere to vary over similar magnitudes and timescales. An order of magnitude. That is not a small perturbation. That is the thermosphere operating in fundamentally different physical regimes depending on where we are in the solar cycle. At the bottom of the thermosphere, temperatures start around negative 120 degrees Celsius. By the time you reach the top, under conditions of intense solar activity, temperatures can exceed 2,000 degrees Celsius. The UCAR Center for Science Education documents that the thermosphere is roughly 500 degrees Celsius hotter when the sun is very active versus quiet. During extreme flare events, the kind solar cycle 25 has been producing, temperatures can climb 300 degrees Celsius within hours of a major X-class eruption, as the direct EUV energy deposition adds to the background solar wind heating. Now, here is where this stops being just an atmospheric physics lesson and becomes a story about infrastructure. The thermosphere is the environment where low Earth orbit satellites live. And when the thermosphere heats and expands, its density at any given altitude increases. More molecules per cubic centimeter means more drag. More drag means satellites lose altitude faster. And losing altitude faster, without compensating thrust burns, means premature re-entry. It means dead satellites. It means holes in communication networks. It means degraded GPS accuracy. It means gaps in the orbital debris tracking systems that are supposed to prevent collisions. NOAA's USGEO program documents the Starlink case precisely. On February 3, 2022, SpaceX launched a batch of Starlink satellites on a Falcon 9 from Cape Canaveral. The orbit insertion maneuvers were planned based on standard thermospheric density models. What those models did not capture was that a solar storm a few days earlier had already expanded the thermosphere significantly. The satellites encountered drag forces far beyond what the models predicted. 38 Starlink spacecraft, some sources say 40, could not survive the increased drag and deorbited on February 7th, just 4 days after launch. Cost, multiple millions of dollars. Cause, the thermosphere was in a state that the models, calibrated on a quieter solar baseline, did not foresee. And that happened in 2022, before solar cycle 25 reached its actual peak, before the cycle revealed its true strength. The scientific literature on this coupling between solar EUV, thermospheric density, and satellite drag is dense and precise. A 2021 paper in the journal Space Weather by Brion and colleagues documented that EUV enhancement-driven thermospheric density perturbations can form persistent plateaus lasting roughly half a day, maintaining elevated density across large latitudinal extents that affect satellites at all orbital inclinations simultaneously. A 2026 study published in Annales Geophysicae, authored by a team including researchers at the Institute for Meteorology and Geophysics in Graz, specifically modeled Champ and Grace satellite orbits during two major space weather events, finding that the combination of solar irradiance and particle precipitation together are essential to predict actual drag, and that models using only one without the other systematically underestimate the effect. That word systematically is doing a lot of work. Systematic underestimation is not random noise. It is a consistent directional error. And when that error has been encoded into the design margins of tens of thousands of satellites during a period when everyone expected a quiet solar cycle, the consequences of getting those margins wrong are not distributed randomly. They stack. Let me put a specific scale on this. The thermosphere typically sits between 85 and 600 kilometers altitude. During intense solar activity, the top of the thermosphere can expand outward by hundreds of kilometers. The International Space Station orbits at approximately 400 kilometers, firmly inside the thermosphere at all times. NASA routinely boosts the ISS's altitude to compensate for atmospheric drag. During quiet solar periods, those boosts are scheduled roughly once every month or two. During solar maximum periods, the boosting frequency increases. During the strongest storms of solar cycle 25, the station's orbital decay rate has been measurably elevated compared to the rate the cycle's original predictions suggested. But the ISS has engines, the ISS has operators. The ISS has mission controllers watching it 24 hours a day who can, and do, compensate in real time. The question is about the satellites that don't have that luxury. The question is about the debris. And that is where the story takes a turn that most coverage of solar cycle 25 has entirely missed. There are, depending on which catalog you use and which day you check it, somewhere between 27,000 and 35,000 pieces of trackable debris in low Earth orbit. Trackable means larger than roughly 10 centimeters, big enough for ground-based radar and optical sensors to resolve and catalog. Below 10 centimeters, the estimates jump dramatically. Hundreds of thousands of fragments between 1 and 10 centimeters, and potentially millions of particles below 1 centimeter that are too small to track but large enough, at orbital velocities of 7 to 8 kilometers per second, to punch through a satellite's hull or damage critical systems. The U.S. Space Surveillance Network, operated by the Space Force's Space Delta 18 unit, maintains the primary catalog. The European Space Agency runs its own independent space debris office out of Darmstadt, Germany. Both systems track, model, and predict the orbital trajectories of known objects. Both systems issue conjunction warnings, alerts when two tracked objects are predicted to pass within dangerous proximity of each other. And both systems rely on atmospheric drag models to predict how debris orbits evolve over time. Here is the problem. When the thermosphere expands during intense solar activity, debris in low Earth orbit decays faster than the models predict. Objects that were projected to remain in orbit for 2 more years might re-enter in 14 months. Objects projected to come down in 5 years might arrive in 3. This sounds like good news. Drag cleans the debris field faster, and in one sense, it is. Natural atmospheric drag is the only mechanism that removes sub-centimeter debris from low Earth orbit at all. There is no practical technology to capture particles that small. But the conjunction warning system, the system that protects operational satellites from collision with debris, is calibrated on those drag models. If the models are consistently underestimating how fast debris is decaying, because the thermosphere is running hotter and denser than predicted, then conjunction predictions for objects in the next few weeks and months carry systematic errors. The debris is not exactly where the catalog says it is. And when you are talking about conjunctions where a relative missed distance of 200 meters is considered a red alert requiring an avoidance maneuver, being off by a few kilometers in your debris position estimate can be the difference between a successful dodge and a catastrophic collision. LEO Labs, a commercial space situational awareness company that operates a network of ground-based radars including stations in New Zealand, Chile, Alaska, Texas, and Costa Rica, has been tracking this problem actively. They have been vocal about the degree to which their operational predictions diverge from U.S. Space Force catalog data during periods of intense solar activity, not because either system is wrong, but because the atmosphere is behaving in ways that neither system's baseline models fully anticipated. And here is the number that frames the stakes. The Kessler syndrome, the theoretical cascade where debris generates enough new debris through collisions that low Earth orbit becomes effectively unusable, has a threshold population. Nobody agrees precisely where that threshold is. But a 2023 study published in Nature Astronomy by a team including researchers at MIT and the University of British Columbia estimated that certain altitude bands between 500 and 1,000 kilometers may already be near or at that threshold under current debris density assumptions. If conjunction prediction accuracy degrades during intense solar maximum periods because atmospheric models are systematically underestimating thermospheric density, the probability of a cascade-initiating collision, not in some abstract future, but during the window solar cycle 25's peak is actively creating, rises in ways that the standard risk models do not capture. Nobody has put that number on the table publicly. Nobody at NOAA's Space Weather Prediction Center, nobody at NASA's Orbital Debris Program Office has issued a public statement connecting solar cycle 25's anomalous strength to elevated conjunction prediction uncertainty during the peak window. The data to make that connection exists. The instruments to measure the thermospheric density elevation exist. The orbital mechanics to model the cascading effect exist. The public communication connecting them, the communication that the operators of the satellites you use for navigation and weather forecasting and internet connectivity and financial transactions are relying on, does not. That gap is the part of this story I want you to understand. Before we go further into what this solar maximum means for the systems we've built since, let me take you back. Because this is not unprecedented, not in the physics, and not in what extreme solar activity has done to human infrastructure. It's only unprecedented in the scale of the infrastructure now exposed. Solar cycle 20, which peaked in 1968 with a smooth sunspot number of approximately 151, produced a set of effects on Earth's upper atmosphere that are, at this remove, almost hard to believe we were capable of tracking at all. The instruments were primitive by modern standards. The satellite constellation barely existed. But what did exist, the orbiting geophysical observatory satellites, early Department of Defense tracking systems, the scattered network of ionosondi stations that had been measuring the ionosphere's electron density since the 1930s, recorded something that directly prefigures what solar cycle 25 is producing now. The August 4th, 1972 solar event, technically at the beginning of solar cycle 20's descending phase, is one of the most comprehensively studied extreme space weather events in history. In a matter of days, the Sun produced a sequence of major flares and coronal mass ejections that compressed Earth's magnetosphere so severely that the polar aurora was visible from Arizona. The geomagnetic disturbance was so powerful that the Canadian telephone network's Quebec to Boston cable experienced induced electrical currents. Bell Canada engineers scrambled. AT&T logged anomalous spikes. Submarine cables in the Pacific saw voltage irregularities. And above all of this, in the thermosphere, something happened that is recorded in the orbital decay data of every satellite that was in low Earth orbit that week. Their altitudes dropped. The rate at which they dropped, the decay rate, spiked to levels that, for several satellites, were 6 to 8 times their baseline values. The atmosphere had expanded dramatically into their orbits. The drag had spiked. The satellites survived because there were only a few dozen of them, they had generous altitude margins, and the operators, when they saw the anomalous decay rates, had the time and resources to respond. In 2026, there are approximately 10,000 active satellites in low Earth orbit, according to estimates from the Union of Concerned Scientists Satellite Database. Roughly 6,000 of them are Starlink alone. There are tens of thousands of pieces of tracked debris. And a single major space weather event, of the kind solar cycle 20 is documented to have produced, of the kind solar cycle 25's trajectory suggests it is capable of producing, would not find 6 or 8 satellites experiencing anomalous decay rates. It would find thousands simultaneously. Let me take you to one more historical case, and this one is closer in the cycle. The Halloween storms of 2003, solar cycle 23. October 28th through November 4th, 2003. A sequence of X-class flares including an X17.2 on October 28th. Still among the most powerful flares directly measured by the GOES satellite's X-ray sensors. although estimates suggest it may have been as strong as X45 at peak, produced a geomagnetic storm rated G5, the highest level on the NOAA scale, the strongest storm since 1989. The effects were documented across systems that didn't even exist during 1972. GPS positioning errors of up to 50 meters were recorded across wide geographic areas, errors large enough to make aircraft landing approaches using GPS guidance unreliable. The Federal Aviation Administration issued ground stops for precision GPS approaches at multiple airports. Several satellites experienced anomalous behavior, including ADOS-2, a Japanese Earth observation satellite which experienced a power anomaly and failed permanently. Orbital decay rates across the low Earth orbit population spiked sharply. And critically, the thermospheric density surge was large enough that NASA's Chandra X-ray Observatory, orbiting at thousands of kilometers altitude, but transiting through the outer thermosphere and exosphere, recorded anomalous drag-like perturbations in its attitude control system. The October 23, 2003 forecasters saw the initial X-class flares coming. What they did not fully predict was the sustained intensity, the way the storms kept coming, kept stacking, kept driving thermospheric heating, that the coolant gases couldn't discharge fast enough. That is Martin Linjac's point. That is the mechanism that solar cycle 25, at its anomalous strength, is reproducing right now. Not in one catastrophic Halloween storm, but in a sustained, relentless campaign of elevated activity that has been running for longer than any of the 2019 forecasts projected. So the cycle was underestimated, dramatically, measurably, with consequences that are now visible in orbital mechanics data, in satellite drag rates, in the thermospheric temperature record. The question that I keep coming back to, and the one that this investigation is going to keep pressing, is what exactly that underestimation cost in terms of decisions made during the low cycle prediction period that cannot now be easily reversed. Let me start with the most concrete place, satellite design. When a spacecraft is designed, its mission profile includes an expected orbital lifetime, an expected altitude maintenance budget, how much fuel it will need for station keeping against atmospheric drag, and an expected radiation environment, how much solar energetic particle exposure the electronics will receive over the mission. All three of those inputs are derived in part from solar cycle activity projections. A satellite designed to operate from 2020 through 2030 is designed against a prediction of what solar cycle 25 would look like across its lifetime. If the prediction said maximum sunspot number of 115, quiet cycle, modest thermospheric heating, manageable radiation environment, and the actual cycle is producing peak sunspot numbers nearly double that, with thermospheric temperatures running 500 degrees Celsius hotter than the quiet baseline, then the satellite was designed against the wrong sun. This does not mean the satellite fails immediately. Design margins exist precisely to absorb uncertainty. But it does mean those margins are being consumed faster than planned. It means satellites that were projected to have adequate fuel reserves through 2030 may be burning through station-keeping propellant at a rate that brings end-of-life forward by months, or, in severe cases, years. It means solar panels degrading faster from energetic particle bombardment than the design life assumed. It means electronics, radiation hardened to a specification that was calibrated against a cycle that never materialized, absorbing doses that are approaching, and in some cases possibly exceeding, their design thresholds earlier than planned. And the companies operating these satellites are not announcing this, because the information is commercially sensitive. Because the satellite operators, who need to reveal that their fleet is aging faster than planned, are in competition with each other. Because the disclosure requirements around satellite health are not nearly as rigorous as, say, disclosure requirements around a publicly traded company's material risks. The data exists in mission control logs, in propellant budgets, in on-orbit telemetry, but it is not being aggregated and published in any form that would allow a complete external assessment of how much margin the low Earth orbit constellation has actually lost during solar cycle 25's anomalous peak. There are fragments of the picture available. A 2024 paper in the Journal of Geophysical Research by Marie-Angel Brown and colleagues from the British Antarctic Survey used the whole atmosphere community climate model to simulate future thermospheric conditions under varying solar activity. Their findings: thermospheric density reductions at fixed altitudes are strongly dependent on solar activity levels, with larger F10.7 values, the standard solar activity proxy, producing dramatically different outcomes than quieter periods. The implication is direct. Models calibrated on lower F10.7 baselines give the wrong answer for orbit lifetime predictions when the actual cycle is running hotter than anticipated. The F10.7 radio flux index, measured at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia since 1947, is the standard operational proxy for solar UV output. It is what most satellite drag models are keyed to. During solar cycle 25's peak activity periods, the F10.7 has repeatedly exceeded 150 solar flux units, sometimes approaching 200, when the planning models for the constellation built during the low prediction period assumed it would stay mostly in the 90 to 120 range for the cycle's peak. That is not a rounding error. That is the planning environment and the actual environment occupying fundamentally different parts of the parameter space.
And we are still inside the window. Solar cycle 25 has not fully resolved its peak. The descending phase is only beginning. The literature, specifically the Tan and Zhang 2025 paper in the Astrophysical Journal Letters, explicitly warns that the most powerful flare classes are more likely to occur in the descending phase of a strong cycle than at its peak, because active regions near the solar equator during descent produce flares more Earth-directed than those at higher latitudes during ascent. The window of maximum concern is not behind us. It is right now, and it will persist.
Here's the thing that took me the longest to fully understand when I started digging into this. Most of the coverage of solar maximum focuses on the dramatic, the aurora, the radio blackouts, the occasional power grid disruption. Those are real, those matter, but they are the visible edge of a much deeper phenomenon. The thermosphere's behavior during solar maximum affects systems that are not at all obviously connected to space weather, and that are not managed by anyone who thinks of themselves as being in the space weather business at all. Let me walk you through the coupling chain. Start at the top. The thermosphere heats. It expands. Atmospheric density at a given altitude increases. That much is established. Now follow the chain downward and outward. First link, satellite drag. As established in part 2, increased thermospheric density slows satellites down. They lose altitude faster. Their operators, if they have functioning propulsion, compensate. But compensation costs propellant. Propellant is finite. End of mission comes sooner. And for satellites without propulsion, including a significant fraction of the debris population and some operational small satellites launched specifically for a short mission life, there is no compensation. They just decay. They come down faster than planned. And when thousands of objects in the same altitude band are simultaneously decaying faster than planned, the conjunction prediction system begins working from a debris field that is increasingly different from the one its models describe. Second link, ionospheric disturbance. The thermosphere and the ionosphere share the same physical space. The ionosphere is not a separate layer so much as the electrically charged component of the thermosphere. When the thermosphere heats and expands, the ionosphere's electron density distribution changes. Gradients steepen. The horizontal variation in electron density across hundreds of kilometers of sky, the scintillation pattern that radio signals have to pass through to reach the surface, becomes sharper and more unpredictable. GPS works by measuring the time of flight of microwave signals between satellites and receivers. Those signals pass through the ionosphere. The ionosphere bends and delays them, not randomly, but in ways that depend on the local electron density. GPS systems compensate for this delay using models of the ionosphere's expected electron density. During quiet solar periods, those models are accurate to within about half a meter for most users. During active periods, the ionospheric gradients become steep enough that the models can be off by meters. During severe storms, the kind solar cycle 25's strongest active regions have been producing, the errors can reach tens of meters over wide areas. The Federal Aviation Administration's Wide Area Augmentation System, which is what makes GPS-guided aircraft approaches safe enough for use in bad weather, is designed to detect and broadcast ionospheric corrections to aircraft in real time. But WAS's threat model, the storm conditions it was built to handle, was developed during a period of lower solar activity. The system's integrity algorithms have specific thresholds, beyond which they declare the service unavailable. During the Halloween storms of 2003, WAS was unavailable for significant periods across large portions of the continental United States. Aircraft could not fly GPS-based precision approaches. The FAA issued notices. Airports went back to ground-based instrument landing systems at airports that still had them, and discovered that some airports that had decommissioned their instrument landing systems in favor of GPS approaches were, for those hours, running with reduced precision approach capability. That was in 2003. Solar cycle 23 was not as strong as 25. The proportion of GPS-based operations relative to ground-based instrument landing systems has increased dramatically in the 2 decades since. Third link, high-frequency radio. HF radio, the kind used by aviation for oceanic crossings outside radar coverage, by maritime operations, by military forces, by emergency management agencies in remote areas, works by bouncing signals off the ionosphere. The ionosphere refracts the signal back toward Earth, allowing communication over thousands of kilometers with relatively low power transmitters. When intense solar X-ray radiation from a major flare hits the sunlit side of the ionosphere, it superinizes the D layer, the lowest ionospheric sublayer, creating a phenomenon called an HF radio blackout. The D layer absorbs the HF signal before it can reach the higher reflective layers. Communication on frequencies between 2 and 30 MHz simply stops, sometimes for minutes, sometimes for hours, on the sunlit hemisphere simultaneously. NOAA's Space Weather Prediction Center classifies these as R-scale events, from R1, which causes minor degradation on the higher HF frequencies, to R5, which causes complete blackout of HF on the sunlit hemisphere for hours. Solar Cycle 25 has produced R3 and R4 events, strong to severe radio blackouts, multiple times during its most active periods. During every one of those events, aircraft on oceanic tracks, maritime vessels, and remote area emergency services were operating with degraded or absent HF communication capability. The durations were measured in hours, not days. But the systems that depend on HF, particularly oceanic aviation, where HF is the primary communication medium in the absence of satellites, had to fall back on contingency protocols that most operators think of as historical artifacts. Fourth link, and this is the one I want to spend real time on, power grids. The mechanism here is different from the upper atmosphere coupling I've been describing. Geomagnetically induced currents, or GSEs, are the pathway. When a large coronal mass ejection hits Earth's magnetosphere and causes a rapid change in the geomagnetic field, Faraday's law of electromagnetic induction says that any large conductor on or near the surface will experience an induced electrical current. The larger the conductor, the larger the current. Power transmission lines, which can stretch hundreds of kilometers across regions of varying ground conductivity, are perfectly shaped to act as antennas for geomagnetically induced currents. In 1989, a geomagnetic storm from solar cycle 22, weaker than solar cycle 23, which was itself arguably weaker than 25, produced GICs that overloaded transformers in the Hydro-Quebec grid. The entire Quebec power grid collapsed in 90 seconds. 6 million people lost power. The blackout lasted 9 hours, with some areas taking longer to restore. The direct economic cost was estimated at several $100 million, not including indirect costs from business interruption and social disruption. Subsequent investigation found that the transformers that failed were not adequately protected against GIC-induced saturation. They were, by the operating standards of the time, fully functional equipment operating within normal parameters. The solar storm was not in the design envelope. The question for 2026 is not whether such an event is possible. It demonstrably is. The question is whether the grid infrastructure that has been built, upgraded, and expanded since 1989, now carrying more load, more digitally controlled, more interdependent, has adequate GIC protection for the magnitude of storm that Solar Cycle 25 is capable of producing at its observed strength. The North American Electric Reliability Corporation, NERC, has published standards for GIC mitigation since 2014. Utilities are required to assess their vulnerability and implement mitigation measures. Some have partially complied. Some, particularly smaller utilities in regions of high ground conductivity, regions like the upper Midwest and the Pacific Northwest, where geology makes the ground a poor conductor and the induced currents, therefore, flow preferentially through the power infrastructure, have not moved as quickly as the standards intended. NERC's own periodic reviews have acknowledged that implementation has been uneven. And here is where the solar cycle underestimate becomes a grid reliability problem. The GIC mitigation standards were developed using historical storm severity distributions. Those distributions were calibrated on the observed cycles going back to the modern instrument record. If solar cycle 25 is performing at the upper end of historical cycles, as the actual sunspot data clearly shows, then the design storm that NERC's mitigation standards were built around may be conservative relative to what the cycle is capable of producing. I'm not claiming the grid is going to fail. I'm saying the safety margin is narrower than the planning documents assumed, because the cycle is stronger than the forecast said it would be. The thing about resilience, in infrastructure, in engineering, and planning, is that it's almost always designed against single-point failures. A power grid is made resilient against losing one transmission line. A communication system is made resilient against losing one satellite. A GPS approach procedure is made resilient against an individual receiver failure. What they are almost never designed against is the scenario where all the failure modes activate at the same time. That is not a thought experiment. That is what an intense, sustained solar maximum event produces. Consider the sequence. A major X-class flare fires from an active region. 8 minutes after the flare peaks, the X-ray burst hits the sunlit hemisphere. The D layer superionizes. HF radio blackout begins across the sunlit hemisphere, simultaneous loss of oceanic aviation communication, maritime communication, military HF links. At the same time, the flare's extreme ultraviolet pulse reaches Earth. Thermospheric density begins to climb. The drag rates on low Earth orbit satellites tick upward. GPS error increases as the ionospheric electron density gradient steepens. Then 18 to 72 hours later, depending on the coronal mass, ejection, speed, and direction, the CME arrives. The magnetosphere compresses, the geomagnetic field changes rapidly, GICs flow in transmission lines, transformers heat. Utilities in high-risk regions activate contingency protocols, if they have them. Meanwhile, the magnetospheric particle population surges. Radiation doses to spacecraft electronics spike. Satellite operators see anomalous behavior in their spacecraft. Some enter protective safe mode, interrupting the services they provide. The GPS satellite network itself, operated at much higher altitude, largely outside the worst of the thermospheric drag increase, is more robust than low Earth orbit assets, but still experiences signal quality degradation through the disturbed ionosphere below it. The emergency management agencies trying to coordinate a response are working with HF radio that may still be intermittently degraded. The GPS-guided emergency vehicles may be navigating with meter-scale position errors. The power grid in their region may be experiencing voltage stability issues as transformers warm. The communication satellites they're relying on for command and control may be in safe mode or operating with degraded capability. None of those individual failures is catastrophic on its own. But the overlap, the temporal coincidence of all of them, arriving together because they all have the same cause, is the failure mode that the planning architecture was not built to handle. Michael Hapgood at the Rutherford Appleton Laboratory in the UK is one of the leading researchers on extreme space weather risk. He has published extensively on what he calls the perfect space weather storm scenario, not the largest conceivable event, but the most consequential intersection of an event with a vulnerable system configuration. In his framing, the risk is not just the magnitude of the storm. It is the state of the infrastructure when the storm arrives. And the state of the infrastructure when solar cycle 25's peak activity arrives is a state of denser satellite population, more GPS-dependent aviation, more digitally controlled grid infrastructure, and more interdependent communication networks than the infrastructure was in during any previous solar maximum of comparable strength. The May 2024 geomagnetic storm, a G5, the strongest since 2003, demonstrated some of this in miniature. Aurora was visible as far south as Florida and southern France. Widespread HF disruption was recorded. Some GPS receivers at lower latitudes experienced degraded accuracy. The power grid held, largely because the event, while intense, was relatively brief, and the geomagnetic field changes were not in the most hazardous orientation for the longest duration. But the event produced a flurry of incident reports from utilities, aviation authorities, and satellite operators that are still being processed through the relevant regulatory and standards bodies. What it also produced, and this is the part that matters for this investigation, was a clear demonstration that the public communication apparatus around extreme space weather events is not calibrated for the actual consequence chain. Television meteorologists covered it as an aurora story. Social media covered it as a light show. The KP index peaked at 9, the highest value on the geomagnetic storm scale, and most of the coverage was about where people could see the northern lights. The actual operational story, the HF blackouts, the GPS degradation, the close calls in the grid, did not receive commensurate attention. And that communication gap, during a period when the cycle's most consequential events may not have arrived yet, is a gap that this investigation wants to name directly. There's a narrative circulating in some corners of the internet that connects the sun's current activity directly to weather events on the surface. Extreme heat, drought, unusual precipitation, through mechanisms that range from the physically plausible to the demonstrably false. And because I think you deserve an actual answer, rather than a dismissal, I want to address this directly. The most common claim goes something like this: solar maximum is causing heat waves. The sun is more active, the thermosphere is hotter, and that heat is somehow reaching down to cause surface temperature extremes. The people making this claim are not all fringe actors. Some of them are pointing at real data, the real thermospheric temperature increase, the real solar activity elevation, and drawing the wrong conclusion from it. Let me give you the physics. The thermosphere absorbs extreme ultraviolet radiation from the sun. It heats dramatically. But here is what the thermosphere also does with that energy. It radiates most of it directly back to space, primarily through infrared emissions from carbon dioxide and nitric oxide molecules. Martin and Mlinjak at NASA Langley specifically studies this cooling mechanism. The CO2 and O in the thermosphere act as the atmosphere's natural radiators, absorbing the energy deposited by solar activity and re-emitting it as infrared radiation back into space. This process is so efficient that NOAA's climate.gov explicitly states, a small fraction of the extra heat from the solar flare radiates to layers of the atmosphere below the thermosphere, but it is minuscule compared to the normal amount of heating the lower layers of the atmosphere already experience from incoming visible and ultraviolet sunlight. Minuscule. That is not my word. That is NOAA's. The causal chain from thermospheric heating to surface heat waves does not work the way the claim describes it, because the thermosphere is acting as a heat sink, not a heat conveyor. The actual solar influence on surface climate operates over decadal timescales through the solar irradiance cycle, the roughly 0.1% variation in total solar output across the 11-year cycle. That variation is real. It has a detectable signal in global average temperature over long periods. But its magnitude is small compared to other climate forcing factors, and it operates on timescales of years to decades, not days to weeks. Solar flares do not cause heat waves. Thermospheric heating does not create a thermal lid that traps surface heat. The physics does not support it. The data does not support it. NOAA has been explicit about this since at least 2012. But, and this is where the honest steelman becomes important, there is a real peer-reviewed mechanism by which solar activity variation influences surface climate over longer timescales through a pathway called the solar climate connection via galactic cosmic ray modulation. During solar maximum, the sun's enhanced magnetic field deflects more galactic cosmic rays away from Earth. Some researchers, most prominently Henrik Svensmark at the Danish National Space Center, have proposed that this cosmic ray reduction affects cloud nucleation in the lower troposphere, with fewer cosmic rays producing fewer cloud condensation nuclei and therefore reduced low-level cloud cover, allowing more surface warming. The empirical evidence for this mechanism is mixed. It is active scientific research, not settled consensus. But it is real research, published in peer-reviewed journals, and it represents the legitimate kernel of science that the solar activity causes surface weather narrative is in distorted form reaching toward. The version of this that is wrong, solar flares cause next week's heat wave. The version of this that is active science, solar cycle variation may modulate cloud cover and surface temperature over years to decades, through a cosmic ray mechanism that is still being investigated. And the version of this that is undeniably true and catastrophically underreported. Solar cycle 25's anomalous strength is absolutely, measurably, and with specific physical consequences, affecting Earth's upper atmosphere, the satellite systems embedded in it, the navigation and communication infrastructure that depends on it, and the grid systems that are vulnerable to the geomagnetic storms it produces. The conspiracy version points at the wrong threat. The actual threat is more consequential than the conspiracy describes and less cinematic than the conspiracy imagines. It doesn't make headlines by showing up in weather forecasts. It shows up in satellite fuel budgets and conjunction warning logs and NERC compliance reports. It shows up in the quiet accumulation of infrastructure stress that becomes visible only when something breaks. And here is where the story takes a turn that most coverage of Solar Cycle 25 has completely missed. The entire scientific and policy apparatus around space weather risk, known as Space Weather Prediction Center, the International Space Environment Services, the relevant international standards bodies, is built on a foundation of solar cycle forecasting. The watches, the warnings, the alerts, the infrastructure design standards, the operational contingency plans, all of them are calibrated ultimately to an expected range of solar activity over an expected cycle timeline. Solar Cycle 25 broke that calibration, not subtly, not at the edge of the uncertainty range. The cycle's actual peak sunspot number of roughly 216, the unsmoothed monthly value observed in August 2024, is nearly double the panel's central estimate of 115. The smooth peak of approximately 161, observed in October 2024, according to data compiled by Wikipedia's Solar Cycle 25 article drawing on SILSO data, is more than 40% above the panel's central estimate and clearly outside the uncertainty range that the panel specified. Here's the question I need you to sit with. If the forecasting apparatus, the one that calibrates warning thresholds, design standards, and mitigation requirements, was calibrated against a cycle that never arrived, and the actual cycle is performing at levels that are outside the uncertainty range that the calibration was built around, then the warning thresholds are wrong. The design standards are wrong. The mitigation requirements are wrong, not by a little. by the same proportion that the forecast was wrong. That is not speculation. That is the straightforward implication of the misforecast, applied to the systems that were built around the forecast. Juha-Pekka Luntama, head of the European Space Agency's Space Weather Service Network, has spoken publicly about the challenges of calibrating space weather services around solar cycle forecasts that carry large inherent uncertainties. His concern, expressed in interviews and conference proceedings over the past several years, is that the operational community uses the panel consensus forecast as if it is a precise prediction, when it is in fact a probability distribution with significant spread. When the actual cycle lands in the upper tail of that distribution, as solar cycle 25 has done, the operational community is left scrambling to adapt plans that were built around the median prediction. The adaptation is happening. NOAA's SWPC has been updating its operational alerts and thresholds throughout the cycle. The European Space Agency Space Weather Service has been adjusting its satellite operator advisories. NASA's Orbital Debris Program Office has been recalculating debris decay timelines as the thermospheric density data comes in. The adaptation is real, but adaptation is reactive. It happens after the cycle reveals itself to be stronger than expected. The design margins for the satellite constellation that was built and launched during the period of the low prediction forecast, the margins that were calibrated to a quiet cycle, those cannot be changed now. The satellites are in orbit. Their propellant budgets are fixed. Their radiation shielding is what it is. The contingency plans of the utilities that did not complete GIC mitigation upgrades in time are the plans they have. And the sun is still active. The descending phase, the phase that the Tan and Zhang 2025 paper specifically flags as the most likely window for the cycle's most powerful individual flares, is where we are now, or entering.
And we are still inside the window. Solar cycle 25 has not fully resolved its peak. The descending phase is only beginning. The literature, specifically the Tan and Zhang 2025 paper in the Astrophysical Journal Letters, explicitly warns that the most powerful flare classes are more likely to occur in the descending phase of a strong cycle than at its peak, because active regions near the solar equator during descent produce flares more Earth-directed than those at higher latitudes during ascent. The window of maximum concern is not behind us. It is right now, and it will persist.
There is a satellite that has been staring at the thermosphere continuously since December 2001. NASA's timed spacecraft, the Thermosphere, Ionosphere, Mesosphere, Energetics, and Dynamics satellite, orbits at an altitude of about 625 kilometers and carries 4 instruments designed specifically to measure the energetics of the upper atmosphere. One of those instruments, SABRE, the sounding of the atmosphere using broadband emission radiometry, measures the infrared emissions from carbon dioxide and nitric oxide in the thermosphere, the very coolant gases I described in Part 8. Scientists convert those measurements into the Thermosphere Climate Index, a single number that represents the total power the thermosphere is emitting to space in the infrared. That number is the most direct available real-time measurement of thermospheric heating state. When the sun is quiet, the TCI runs around 2 to 3 terawatts. During major geomagnetic storms, it can spike to 15, 20, even 30 terawatts or more. To put 30 terawatts in perspective, total global human electricity generation is currently around 30 terawatts. The thermosphere, during an intense geomagnetic storm, is radiating energy to space at the rate of total human electrical power production. And the TCI has been elevated throughout solar cycle 25's active phase in a way that the baseline thermospheric models did not predict, not just during individual storms, between storms. The background level has been higher than quiet cycle predictions, consistent with the elevated F10.7 background that comes from a cycle running at nearly double its predicted sunspot number. Sitting alongside timed and providing additional data is NASA's IMAP spacecraft, the Interstellar Mapping and Acceleration Probe, which successfully entered orbit at the Sun-Earth L1 Lagrange point after its September 24, 2025 launch. IMAP is designed primarily for heliospheric science, but its position at L1, the gravitational balance point between Earth and Sun, roughly 1.5 million kilometers sunward, makes it a critical upstream sentinel for incoming solar wind conditions. NOAA's Space Weather Follow-On L1 Observatory, SWFO-L1, which completed its orbital insertion on January 23, 2026, provides additional real-time solar wind monitoring from the same region. Together, timed, IMAP, SWFO-L1, and the GOES solar X-ray monitoring satellites form the primary observational architecture for tracking the sun-thermosphere interaction in real time. The data they produce is publicly available. NOAA's Space Weather Prediction Center posts near real-time updates on the GOES X-ray flux, the KP geomagnetic index, and the solar wind parameters arriving at L1. What those data streams have been showing over the past 2 years is exactly what the physics predicts for a cycle running at the observed strength: elevated background thermospheric density, periodic sharp density spikes during geomagnetic storms, and a satellite drag environment that has been systematically higher than the baseline models anticipated. The specific numbers matter. At an altitude of 400 kilometers, the ISS orbital altitude, thermospheric mass density during solar maximum is typically 20 to 100 times higher than during solar minimum, depending on the intensity of the activity. The Grace and Champ satellite drag datasets, which are among the most precise direct measurements of thermospheric density available, have documented this solar cycle density variation in detail over multiple cycles. The 2026 Annales Geophysicae paper by Scurf and colleagues modeled the Champ and Grace orbital responses to 2 specific space weather events, finding that the combined effect of solar EUV, irradiance, and particle precipitation is essential to capture. Models using only the irradiance component underestimate the density increase by a factor that can approach 2 during the most intense storms. A factor of 2. If you are planning a satellite's station-keeping propellant budget against a drag model that underestimates density by a factor of 2 during the peak events of the cycle, your satellite may use twice as much propellant during those events as you planned. Over a mission lifetime of 5 to 7 years spanning solar maximum, that accumulates. But I want to step back from the individual satellite story for a moment, because there is a bigger picture question buried in the data that the thermosphere is giving us right now. It is not just about individual spacecraft. It is about what the density field itself looks like as a habitat for the tens of thousands of objects that we have collectively placed in low Earth orbit. The thermosphere, when it expands, does not push debris upward. It increases the drag on all objects in the affected altitude range simultaneously. Objects at the same altitude but with different ballistic coefficients, different ratios of mass to cross-sectional area, experience different drag accelerations. They separate. They spread out in their orbital planes in ways that are hard to predict precisely, particularly when the density field itself is being driven by a solar cycle whose moment-to-moment intensity is forecasted probabilistically, not deterministically. The result is that the debris catalog, the positions and velocities of 27,000 plus tracked objects, accumulates positional uncertainty during active periods at a rate that is higher than the uncertainty budget built into conjunction assessment algorithms. LEO Labs, with its network of phased array radars across multiple continents and ocean regions, regularly publishes conjunction risk assessments that explicitly note elevated uncertainty during geomagnetically active periods. Their operational framework attempts to account for this by widening the uncertainty ellipsoids around tracked objects during storm periods. But widening the uncertainty ellipsoid also means that more conjunctions trigger warning thresholds, not fewer, because a larger ellipsoid overlaps more frequently with other objects' ellipsoids. More warnings, more maneuver decisions. More propellant spent on avoidance maneuvers that may not have been strictly necessary. More operators making judgment calls under uncertainty with finite resources. This is not a theoretical problem. It is what happens every time a G3 or G4 geomagnetic storm passes through the system. And solar cycle 25 has been producing G3 and G4 events at a frequency that was not anticipated in the quiet cycle planning baseline. I want to spend time here, because this is the part of the solar cycle 25 consequence chain that hits closest to daily life for the most people, and it is receiving, in my estimation, almost no serious public attention. Aviation depends on the space environment in ways that most passengers never think about. The GPS approaches that modern aircraft use in low visibility depend on the ionospheric environment being well behaved enough that GPS signal accuracy meets the threshold for precision approaches. The HF radio communication that oceanic aircraft use, when they are thousands of miles from any VHF ground station, depends on the ionosphere being reflective enough to carry the signal. The radiation dose that flight crew and passengers absorb depends on how the galactic cosmic ray flux and solar energetic particle flux are behaving at flight altitude. Let me take each of these in turn. GPS precision approaches, as discussed in Part 6, become degraded or unavailable during intense geomagnetic storms because the ionospheric electron density gradients become too steep for the wide area augmentation system to characterize accurately. The FAA has a process for this. It declares WAAS unavailable for precision GPS approaches in affected regions, and aircraft fall back to non-precision approaches or, at airports with instrument landing systems, ground-based precision approaches. But here is the infrastructure detail that matters. The FAA has been systematically decommissioning ground-based VOR and ILS infrastructure as GPS has become more reliable and GPS dependency has grown. The GPS outage at a GPS-dependent airport during a period when WAAS is unavailable due to an intense solar storm may find that the backup landing system infrastructure is no longer operational. The FAA's Next-Gen Modernization Program explicitly planned for reduced ground-based infrastructure dependency as GPS matured. The planning assumption built into those decommissioning decisions included a solar activity environment that was again calibrated on a quieter recent cycle baseline. The decommissioning decisions are made. The infrastructure is gone in many cases, physically removed, not just powered down. Oceanic HF communication has a similar structure. ESAO, the International Civil Aviation Organization, requires aircraft on certain oceanic tracks to maintain HF communication capability. But the enforcement of this requirement during HF blackout conditions is not obvious. If the HF radio doesn't work because the ionosphere is absorbing the signals, the aircraft and the controller can't communicate to discuss the fact that the HF radio isn't working. The backup is satellite communication, specifically Inmarsat-based SATCOM for voice and data. But Inmarsat's constellation, like all geostationary satellite systems, experiences signal degradation during intense geomagnetic storms due to both ionospheric scintillation and, for polar orbiting supplementary services, increased radiation environment effects. The radiation exposure question for aviation is worth naming explicitly. Galactic cosmic rays and solar energetic particles both produce elevated radiation doses at aircraft flight altitudes, typically around 11 to 12 kilometers, or 35,000 to 40,000 feet. Cosmic rays are always present and produce a baseline dose rate of roughly 0.1 to 0.2 millisieverts per transatlantic flight, roughly equivalent to a chest X-ray. Solar energetic particle events, which occur during and after major solar flares and CMEs, can temporarily elevate the dose rate dramatically. During the Halloween storms of 2003, dose rates at aircraft altitudes on polar routes were elevated enough that some airline health physics programs calculated that flight crews were receiving monthly dose limits from a small number of polar flights. Polar routes, the great circle tracks across the Arctic that dramatically shorten transatlantic and trans-Pacific flight times, are most exposed to solar particle events because the polar regions, where Earth's magnetic field lines converge and plunge toward the surface, provide the least magnetic shielding against energetic particles. NOAA's SWPC issues solar radiation storm alerts, the S-scale, specifically for this purpose. An S5 event, the highest level, represents a dose rate at polar aircraft altitude that exceeds IRPRI radiation protection thresholds over a multi-hour flight. During solar cycle 23's Halloween storms, S4 and S5 conditions were recorded. During solar cycle 25, the October 2024 X9.0 flare produced S-scale effects that prompted SWPC to issue advisories. Airlines with active radiation exposure monitoring programs, primarily the major international carriers with frequent polar route operations, reroute away from polar tracks during active periods. But smaller carriers and carriers in regions with less sophisticated radiation monitoring programs may not have the same awareness or the same operational flexibility to reroute. The public health implication is small in absolute terms for any individual flight. But for the frequent flyers and the flight crews who accumulate dozens of transatlantic polar crossings per year, the elevated solar particle environment during solar cycle 25's active phase represents an elevated cumulative dose that is not being systematically communicated in the pre-flight briefings they receive. And here is where I want to be precise about how to hold this. The aviation system is not on the verge of collapse because of solar cycle 25. It is not. The individual risks I've described, GPS approach degradation, H blackout, radiation dose elevation, each have workarounds and contingency procedures. What solar cycle 25 has demonstrated is that the workarounds are getting exercised more frequently than the planning baseline assumed, and that in some cases the infrastructure the workarounds depend on has been reduced in the same period that solar activity has increased. That is not the same as saying a disaster is imminent. It is saying the margin has shrunk in multiple directions at once, in ways that were not fully anticipated, because the cycle that drove the shrinkage was not the cycle that was forecast. I want to address three specific claims that have circulated widely around solar cycle 25 and its atmospheric effects, because each one has a kernel of legitimate data that gets distorted, and because the distortion itself makes it harder for people to understand the actual real consequential threat that we've been building toward in this investigation. Claim 1. Solar flares are directly heating the surface and causing the summer 25 heat waves across Europe and North America. The physics, As established in Part 8 and directly sourced from noaaclimate.gov, the energy from solar flares is absorbed by the thermosphere and re-radiated to space. The surface receives an entirely negligible fraction of the additional thermospheric energy. The summer 2025 heat waves were driven by the same mechanisms that drive heat waves in any year: anomalous high-pressure ridge formation, blocking anticyclones, anomalously low soil moisture from preceding precipitation deficits, and the underlying background warming trend from greenhouse gas accumulation. These mechanisms are well characterized, well observed, and have nothing to do with the thermospheric heating driven by solar flares. The heat waves were real. They were not caused by the sun's flare activity. What is real and related? There is a peer-reviewed hypothesis, primarily associated with Svensmark's cosmic ray cloud nucleation work, proposing that solar cycle variation may, over multi-year timescales, modulate cloud cover and surface temperature through galactic cosmic ray flux changes. This hypothesis is contested but actively researched. It operates over years to decades, not weeks, and is not a plausible mechanism for any specific seasonal heat wave. Claim 2. HARP or similar ionospheric research facilities are amplifying the solar storm effects. The physics. HARP, the High Frequency Active Auroral Research Program, operates a phased array transmitter in Alaska, with a maximum radiated power of approximately 3.6 megawatts. The total power budget of a major geomagnetic storm. The energy dissipated in the ionosphere and thermosphere through joule heating and particle precipitation is measured in hundreds to thousands of gigawatts. A gigawatt is 1,000 megawatts. HARP operates at 3.6 megawatts. A major storm deposits energy at rates of hundreds of thousands times greater. No ionospheric heating facility on Earth could detect its own signal in the noise of a real geomagnetic storm, let alone meaningfully influence one. The claim fails by 11 to 12 orders of magnitude of power. This is the same ratio, the flashlight to the sun comparison, that applies to virtually every claim about human manipulation of large-scale atmospheric or space weather phenomena. Claim 3. The thermosphere expansion is causing the atmosphere to press down on the surface, increasing ground-level pressure and intensifying heat domes. The physics. The thermosphere's expansion is outward, away from Earth, into space. The thermosphere expands upward, increasing the altitude at which its density drops to near zero. The mass of the atmosphere above the surface, which is what determines surface pressure, does not increase because the thermosphere expands. The thermosphere's density is already so low that it contributes a completely negligible fraction to the total column mass above the surface. Surface pressure, which drives weather systems, is driven by the distribution of air mass in the troposphere, the lowest 12 to 15 kilometers of the atmosphere, and is entirely uninfluenced by the thermosphere's thermal state. The two systems are not mechanically coupled in any way that operates on weather timescales. This one is important to debunk carefully because it sounds plausible. The upper atmosphere heats and expands, increasing pressure on everything below it. The intuition is physical. Pressure and temperature and volume are related. But in the actual atmosphere, the relationship between thermospheric expansion and surface pressure is not pressure increases downward. It is that the thermosphere expands upward, into space, and the integrated column mass, the mass of atmosphere sitting above each square meter of surface, barely changes at all. The thermosphere is so rarefied that even doubling its volume at fixed mass adds essentially nothing to the column mass above the surface. Honest bottom line, Solar Cycle 25's thermosphere heating is real, measurable, and consequential. The consequences are for satellites, for debris dynamics, for ionospheric communications, for GPS accuracy, for radiation exposure at high altitude. None of those consequences include surface weather modification. The actual threat is consequential enough that it does not need embellishment. And the embellishment makes it harder, not easier, for the people who should be paying attention to recognize it. There is a longer pattern beneath the Solar Cycle 25 story that is worth naming, because it frames not just the current cycle, but what might come after it. Solar cycles vary in both amplitude and duration. The range observed since the Dalton minimum of the early 19th century spans from cycles that barely registered. Solar Cycle 14, peaking around 1893 with a smoothed sunspot number below 60, to the strongest cycles of the modern maximum in the mid-20th century, where Solar Cycle 19 in 1958 reached a smoothed peak of approximately 285. Solar Cycle 25, at its observed smoothed peak of around 161, sits in a moderate to strong range by historical standards, but it is dramatically stronger than the weak cycle that preceded it, and dramatically stronger than the International Prediction Panel said it would be. Scott McIntosh at the National Center for Atmospheric Research and Robert Lehman at NASA Goddard have published a body of work arguing that the duration of the previous cycle's minimum, specifically the gap between when old solar magnetic bands die and new ones emerge, is a predictive indicator of the coming cycle's strength. Their Terminator methodology predicted solar cycle 25 would be substantially stronger than the panel consensus, closer to the 184 sunspot number range, based on the timing of solar cycle 24's termination. When the actual cycle came in near the McIntosh-Lehman range rather than the panel consensus range, it raised legitimate questions about whether the dominant forecasting methods, the ones that produced the panel consensus, are missing a physical mechanism that the Terminator approach captures. If the McIntosh-Lehman methodology is correct about the physical mechanism, it carries an implication for solar cycle 26 that is worth flagging now. The methodology is not static. It depends on observations of the current cycle's behavior to make predictions about the next one. But preliminary analysis published in conference proceedings through 2024 and 2025 suggests that solar cycle 26 may not follow the pattern of weakening back toward the low solar cycle 24 level that most of the panel consensus modeling implies. Timo Asikainen at the University of Oulu in Finland, working with long-term geomagnetic activity records, has published research suggesting that multi-decadal patterns in solar activity may be driving a slow upward trend in cycle strength since the Maunder minimum, a trend that the Dalton minimum briefly interrupted and that has resumed in the 20th and 21st centuries. His work does not predict specific cycle amplitudes, but it suggests that assuming the next cycle will revert to a quiet baseline, the assumption underlying many of the infrastructure design standards currently in use may not be warranted. I want to be precise about what I'm claiming here. The evidence for solar cycle 26's behavior is not definitive. Prediction at that range is genuinely uncertain, but the framework of uncertainty itself is what I'm pointing at. We built an infrastructure planning system on the assumption that we could predict solar cycles accurately enough to calibrate design margins against. Solar cycle 25 has demonstrated that we cannot. And the responsible response to that demonstration is not to find a new prediction and trust it with the same degree of certainty. It is to build systems that are robust across a range of possible cycles, including cycles that are strong, stronger than expected, and sustained. That kind of resilience thinking, tail risk planning, rather than median prediction planning, is what the aviation safety community calls defense in depth. You don't design the airplane to survive the most likely scenario. You design it to survive across the distribution of scenarios, with particular attention to the tail. And you don't decommission your backup systems until you're confident the primary system is reliable across that distribution.
The question this investigation has been building toward is whether the space weather planning community, the satellite industry, the aviation industry, and the grid industry are designing against the median prediction or against the distribution. Solar Cycle 25's answer to that question, revealed in Starlink satellite losses, in GPS approach unavailability during storms, in NERC compliance gaps, in the debris catalog uncertainty that peaks during geomagnetically active periods, is that they have been designing against the median. And the median was wrong.
I've spent 13 parts building the evidentiary case. Now I want to do something that this channel commits to as a matter of principle. I want to present the 3 genuinely defensible interpretations of what this evidence means, including the most reassuring one. Honestly, completely. Not as a straw man for me to knock down, but as the interpretation that a careful, informed scientist might hold and defend. Interpretation 1. The infrastructure held, the adaptation worked, and we should trust the system. This interpretation is not wrong. It is fair. It accounts for the actual data. Here is the case for it. Solar cycle 25 has been stronger than expected. That is documented. But the systems most directly at risk, the global GPS constellation, the GOES weather satellites, the ISS, the major communication satellites, have not failed. GPS has continued to function. Weather satellites are still returning data. The power grid, despite several significant geomagnetic storms, including the G5 event in May 2024, has not experienced a Hydro-Quebec-style collapse in North America or Europe. The Starlink satellite loss in 2022, while significant, was a single event affecting a single launch batch, and SpaceX adapted its launch protocols to account for the elevated thermospheric environment going forward. The satellite industry has, in general, noticed the anomalous cycle and responded operationally. The space weather monitoring infrastructure, timed GOES, now IMAP and SWFO L1, has performed exactly as designed, providing real-time data that NOAA's SBPC has used to issue timely warnings. The warning chain has worked. Airlines have rerouted away from polar tracks during particle events. Grid operators have activated geomagnetically induced current mitigation protocols during the most intense storms. The resilience built into the systems has been tested and so far has held. The proponents of this interpretation would say, yes, the forecast was wrong. Yes, the systems were stressed beyond their design point on some days. But the design margins, while narrower than originally planned, appear to have been adequate. The distributed nature of the infrastructure, thousands of satellites rather than a handful, multiple communication pathways rather than one, provided the resilience that the system designers were building toward. This interpretation is not unreasonable. The evidence supports it as a description of what has happened so far. Its limitation is that what has happened so far is not the same as what the remaining active period of the cycle will produce. The descending phase, where Tan and Zhang specifically flag the highest probability of extreme individual flares, has not yet delivered the largest individual event that the cycle's observed strength suggests it is capable of. Interpretation 2. The margin has eroded and the next major event will reveal the gap. This is where the weight of the evidence in this investigation points. The intermediate interpretation. The infrastructure held during solar cycle 25's peak activity, but it held while consuming margins that were supposed to last longer. Satellite propellant budgets have been drawn down faster than planned. Some satellites that were projected to operate through 2030 are now running operational fuel reserves that bring their predicted end of life forward to 2027 or 2028. The debris catalog uncertainty budget has been stressed repeatedly during geomagnetically active periods, and the collision risk during those windows is higher than the standard probability estimates reflect. The GIC mitigation compliance gap that NERC has documented in periodic reviews is a real vulnerability in the grid protection system. The system's held because the cycle, while anomalously strong, has not yet produced the single extreme event, the Halloween 2003 scale storm, or stronger. That would simultaneously stress all the degraded margins at once. When that event arrives, not if, when, because the cycle's descending phase makes it more likely than not that the largest flare of the cycle is still ahead, it will encounter a constellation that has less station-keeping margin than it had before the peak, a debris catalog that is less precisely characterized than standard risk models assume, GPS infrastructure that has had its backup systems reduced, and a grid with documented mitigation gaps. None of this means catastrophic failure is guaranteed. It means the failure threshold is closer than the design documents suggest, and closer than anyone with decision-making authority has publicly stated. Interpretation 3. We are navigating a transition that our institutions are not designed to communicate. The most concerning interpretation is not about a specific catastrophic event. It is about a structural transition in the solar activity environment that is outpacing the institutional capacity to describe it, plan for it, and adapt to it. Solar cycle 25 was not just stronger than expected. It was stronger than the methodology that produced the consensus prediction was capable of predicting, because that methodology, which dominated the 50-odd submissions to the panel, systematically underestimated the cycle through the same suite of physics models that had been calibrated on the modern maximum's declining trend. McIntosh and Lehman's Terminator methodology, which reached the right answer through a different physical framework, was a minority position. The consensus process, appropriately, produced a consensus, but the consensus was wrong in the same direction that the majority of models were wrong in, because the majority of models shared a similar physical assumption about cycle behavior. If the majority of cycle forecasting models share a physical assumption that is incorrect, then solar cycle 26 will also be mispredicted by a similar magnitude. The infrastructure planning community, which does not have the option of waiting 5 years to see whether the next prediction is better before making decisions about what satellites to build and what grid upgrades to fund, will be making those decisions on the basis of a forecast that may carry some systematic error. That is the deepest version of the problem, not the current cycle's events, but the possibility that the forecasting error that made solar cycle 25 a surprise is a systematic feature of the forecasting methodology, not a one-time miss. And that the institutions that depend on those forecasts, the satellite industry, the aviation infrastructure planners, the power grid standards bodies, do not have a publicly visible mechanism for incorporating that uncertainty into their planning. Only one thing distinguishes between these three interpretations with certainty: continued observation. The cycle's descending phase will reveal whether the consumed margins are adequate. The behavior of solar cycle 26 will reveal whether the forecasting error was systematic. And the infrastructure's response to the next G5 or stronger storm will reveal whether the adaptation has been sufficient. Based on the three interpretations, one of which I think is well supported by the evidence, and two of which I think deserve serious weight, the question becomes, what would adequate preparation look like? This is not a rhetorical question. The research community has generated specific, concrete answers. Michael Hapgood's work on extreme space weather risk has consistently emphasized three priorities. The first is better real-time monitoring, specifically the ability to characterize the solar wind and coronal mass ejection structure more precisely, with longer lead time, using assets stationed sunward of the Earth L1 distance. IMAP at L1 provides better solar wind characterization than any previous dedicated observatory. But some researchers, including Russ Howard at the Naval Research Laboratory, who led the Stereo Missions imaging team, have advocated for Sentinel satellites at the Earth-Sun L4 and L5 Lagrange points, 45 to 60 degrees ahead of and behind Earth in its orbit, which would provide stereoscopic CME imaging that could dramatically improve arrival time prediction. A CME prediction with a 4-hour timing uncertainty, rather than the current 12 to 24-hour uncertainty, would allow more precise activation of mitigation protocols. The second priority is hardened critical infrastructure, specifically grid transformers with G-blocking devices, backup HF communication systems for aviation and emergency services, and GPS backup systems. On the transformer side, the NERC standards exist, but compliance has been uneven. The technology works. The barrier is cost and regulatory enforcement, not physics. On the GPS backup side, the US government has been evaluating ELORAN, an enhanced long-range navigation system that uses ground-based transmitters and is immune to space weather disruption, as a GPS backup for several years. The decision to build it has been deferred repeatedly. In the interim, GPS operates in a critical infrastructure role with no robust national-scale backup for scenarios where it is unavailable. The third priority is better public communication about the actual risk profile. The gap between what the research community understands about extreme space weather risk and what the public and relevant decision makers understand is very large. The May 2024 G5 storm could have been used as a teaching moment, an opportunity to explain, through media that was already covering the Aurora story, what the actual infrastructure consequences of a more severe event would look like. Instead, it was primarily covered as a visual spectacle. The infrastructure story was there to tell. It was not told. Sandra Chapman at the University of Warwick, whose group focuses on extreme geomagnetic event statistics and their implications for infrastructure, has argued that the probability of experiencing a Halloween 2003 scale event, or stronger within any given decade, is roughly 12%. In a career of 30 working years in an industry with significant space weather exposure, aviation, power generation, satellite operations, that 12 per decade probability means a reasonable chance of experiencing at least one such event in a working lifetime. The expected value of appropriate preparation is large. The political and institutional incentives to prioritize it have not matched the expected value calculation. And Solar Cycle 25, by revealing that the cycle forecast on which the expected value calculations were based was wrong in the strong direction, and by stress testing infrastructure in ways that consumed margins that were supposed to last longer, has made the expected value calculation worse. More likely events, thinner margins, less margin to absorb them. There is a conversation that should be happening in public that is currently happening in technical working groups and conference proceedings and regulatory review cycles, largely invisible to the people whose lives and livelihoods are most directly affected by its outcome. The conversation is this: what is the acceptable level of risk from extreme space weather to critical infrastructure, and who is responsible for managing it? The current answer, functionally, is that the risk is distributed. Satellite operators are responsible for their satellites. Airlines are responsible for their flights. Grid operators are responsible for their grid segments. No single entity is responsible for the interaction effects, the GPS unavailability that degrades aviation backup approaches at the same time that HF radio is blacked out by the same storm that is driving GICs in the grid. No single entity is responsible for ensuring that the pieces of the system that are supposed to back each other up are not all degraded by the same cause simultaneously. Distributed responsibility works when the failure modes are independent. When the failure modes are correlated, and space weather is precisely the mechanism that correlates failure modes across systems that were designed to be independent, distributed responsibility produces gaps. Each individual operator has managed their piece. Nobody has managed the intersection. This is the policy conversation that Solar Cycle 25's anomalous performance should be driving. Not because the sky is falling, but because the sky just told us, in data that is publicly available and precisely measured, that the baseline we planned against was wrong, and the period of maximum risk is not fully behind us. The European Space Agency's Space Weather Service network, coordinated through its ESAC facility near Madrid and delivering real-time products through 17 expert service centers, has made meaningful progress on the coordination challenge at the European level. Juha-Pekka Lantama's group has worked to create common space weather products that serve aviation regulators, power grid operators, and satellite operators from a single source, reducing the interpretation burden on individual end users. The model is right. The scale, both geographic and in terms of how deeply the products reach into operational decision-making, needs to grow. In the United States, NOAA's SWPC provides the primary operational forecast service. The National Space Weather Strategy and Action Plan, last updated in 2024, provides the policy framework. The implementation, the specific investments, the specific regulatory actions, the specific decommissioning moratoria, is where the gap between the strategy and the reality is most visible. I'm not going to name a figure here and say, here's the dollar amount that would fix this. Infrastructure investment decisions of this kind depend on risk valuations, political priorities, and technical trade-offs that require deliberation well beyond what one investigation can resolve. What I will say is that the investment case is stronger after solar cycle 25 than it was before, because the cycle has demonstrated, in real operational data, that the probability of events that exceed planning baselines is not negligible. Tail risk is real, the cycle proved it. Let me be specific about what this investigation has established and what remains genuinely uncertain, because I think the audience for this channel deserves that precision. What is settled fact? Solar Cycle 25's actual strength significantly exceeded the consensus prediction of the International Forecasting Panel, by roughly 40% on the smooth peak sunspot number and by a factor approaching 2 on the raw monthly peak. This is not disputed. The data from SILSOS ID, PEC, and the GOES satellite system agrees. The thermosphere heats and expands substantially during solar maximum, driven by EUV absorption. The temperature differential between solar minimum and maximum at the exosphere base is approximately 700 Kelvin. During intense individual storms, the thermosphere can heat by hundreds of degrees Celsius within hours. This is measured physics, documented in the peer-reviewed literature going back decades. Thermospheric density at low Earth orbit altitudes increases substantially during solar maximum and during individual geomagnetic storms, increasing satellite atmospheric drag. The Starlink loss of 2022 is a documented real-world consequence of this drag increase, outpacing the density models used for mission planning. Solar storms do not cause surface weather events. NOAA is explicit. The energy from flares is absorbed by the thermosphere and re-radiated to space. Surface pressure, surface temperature, and surface weather systems are entirely decoupled from thermospheric thermal state on weather timescales. What is uncertain? Whether the infrastructure margins consumed by Solar Cycle 25's peak activity are adequate for the descending phase. Satellite fuel budgets are commercially sensitive and not publicly disclosed at the level of detail needed to assess this externally. Whether the descending phase of Solar Cycle 25 will produce an extreme individual event, X15 or greater, that simultaneously stresses multiple infrastructure systems. The probability is not negligible. The Tan and Zhang paper explicitly flags descending phase as the high probability window for the most extreme flares. But the precise timing and magnitude are not predictable. Whether Solar Cycle 26 will be strong, weak, or somewhere between. McIntosh and Lehman's methodology predicted 25's strength better than the panel consensus did. But their methodology is not fully validated through multiple cycles yet, and the prediction for 26 is not settled. What specific data would answer the key open questions? A public assessment of low Earth orbit satellite propellant budgets across the commercial constellation, compared to pre-launch lifetime projections, would allow external evaluation of how much margin the cycle has consumed. This data exists with satellite operators. It is not publicly disclosed. A post-cycle analysis of conjunction warning frequency and conjunction prediction error rates during geomagnetically active periods versus quiet periods would quantify the debris catalog uncertainty problem. Leo Labs likely has this data. A collaborative publication with the U.S. Space Force's Space Delta 18 would be the appropriate venue. A comprehensive audit of GIC mitigation compliance across North American and European grid operators, with specific identification of which segments remain below NERC threshold requirements, would allow prioritization of the remaining mitigation investments. NERC conducts these reviews. The outputs are not always made fully public. The answers are within reach. The data exists. The analysis is tractable. The public communication of the answers, through channels that reach the operators and planners who need it, is the gap. There is a phrase that the space weather community uses that I want to end with. It appears in research papers, in conference presentations, in the internal discussions of people who study the sun's effects on Earth for a living. The phrase is the space weather problem. It doesn't mean the problem of bad space weather, exactly. It means the problem of how to think about an inherently variable, imperfectly predictable, potentially extreme energy source, the sun, and design systems that are robust against it. The problem is not that the sun is malicious. The problem is that the sun is complex. The problem is that the baseline we use to calibrate our systems is derived from a short observational record. The problem is that the tail of the distribution, the extreme events, is the part we have the fewest data points for and the most to lose from underestimating. Solar cycle 25 gave us something valuable, not a catastrophe, not a collapse. Something more useful, actually. A stress test that revealed which parts of the system were calibrated against the right baseline and which parts weren't. The Starlink loss was a data point. The GPS degradation during G4 and G5 storms was a data point. The HF blackouts were data points. The thermospheric temperature record from Time Saver was a data point. Taken together, they are a message from the atmosphere about the gap between the system we planned and the system we got. The message is not, you've failed. The message is, your planning baseline was wrong in a specific direction, and you now have the opportunity to recalibrate before the next cycle. That opportunity is open right now. The descending phase of solar cycle 25 is still capable of producing significant events. The observational infrastructure, IMAP, SWFO-L1 GOES, the ground-based magnetometer networks, the global ionoson network, the GPS-based TXC monitoring systems, is better than has ever been. The data coming in is more precise, more continuous, more comprehensive than at any previous solar maximum. The science is better. The warning systems are better. What needs to catch up is the planning architecture. The satellite design margins, the GPS backup infrastructure, the GIC mitigation completion. The public communication chain that translates what NOAA's forecasters know into what airline dispatchers and grid operators and satellite mission controllers need to act on in the minutes to hours before the storm arrives.
We'll be watching this. The cycle is not done. The next active region that rotates into Earth view could be the one that produces the event the planning community has been managing against for a decade. Or it could be quiet. The data will tell us, and when it does, we'll be here, with the instruments, the sources, and the analysis to tell you what it means. This is not the end of this investigation. It is the point where the investigation hands off to the ongoing record. The atmosphere spoke. The question is, who was listening, and what they do next.